Okay. So welcome everyone. So today we have Professor Jane Greaves from Cardiff University. And then for those who do not know Jane, I'm going to introduce her. So Jane did her PhD at Queen Mary University of London. And then she spent some time in several universities in the UK and observatories, working as a postdoc. And then her first tenure track fellowship or position, tenured academic post, was with Scottish Universities Physics Alliance. And right now she is a professor at Cardiff in the School of Physics and Astronomy. So thank you very much, Jane, again, for joining us today, and the floor is yours.
Great, thank you very much. I hope you can hear me okay.
Yes, we can, yes.
Great. So it's a pleasure to speak to a group of astrobiologists in particular. So let me get on to telling you about our discovery of phosphine in the clouds of Venus. Okay, just to introduce the team, this is the whole team. We're not a very big group. We came together for this project, a lovely diverse team from UK universities and the US and also in Japan. Okay, so I got interested in phosphorus about 10 years ago, actually, through teaching undergraduates. I was interested in the idea of the chemical elements that are important for life. And to my surprise, I found that phosphorus has only been measured systematically in stars like the sun in a paper in 2011. And I thought, that seems crazy, because phosphorus is really important for planetary chemistry and for life, particularly as a major atom in the DNA molecule, for example. So how can we know so little about it? And even now, there's not much known about its path from its origins in supernova explosions. On the left, I'm working with a master's student here on only the second set of observations of phosphorus produced in a supernova remnant. And then we know a little bit more about the path of the phosphorus atom through space, in part due to Isaskun's work, very thoroughly looking at the chemistry. And then she and I are collaborating on the first project to try and detect phosphorus-bearing molecules in a planet-forming disk. And this is an artist's impression of that disk on the right-hand side. So it's very intriguing to find that this molecule without which, this atom without which there possibly isn't life, is so little understood in the astronomical sense. So the Venus project was really not part of this original plan. It came about because I was asked to look into some solar system observations that might be performed by this future far infrared space telescope called SPICA, which is a possible ESA mission. And it's a spectroscopic mission largely, so I was looking at what had been done spectroscopically for the solar system, for example, going back to the late 1990s with the ISO spacecraft. And one of the things ISO did was study phosphine in the atmospheres of Jupiter and Saturn. And I didn't know much about this, but I thought, well, a much more modern telescope, presumably you could look at much smaller planets, the rocky planets. And then I discovered, of course, that was very naive. So there is phosphine in the atmospheres of Jupiter and Saturn, but it's dredged up from layers far down in the dense atmosphere, which are hot and very hydrogen rich. And so it's a perfectly natural product which just appears at the surface through upwelling. And that's not at all the situation on rocky planets, such as the Earth, for example. So if you have an atmosphere like the Earth, or indeed the upper clouds of Venus, it's very, very poor in free hydrogen, and it's relatively cool. And so phosphine is not a natural chemical product. And in fact, on Earth, it is a very distinctive biosignature. It is sometimes made industrially. I think it's for fumigation, but it's very toxic to larger life forms like us, so it's not much used. But it is produced by anaerobic bacteria, microorganisms, and it's not entirely understood why. It may just purely be a waste product, or it might be even they use the toxicity, and this is not really my subject of expertise, but perhaps to destroy surrounding organisms of a different kind, something like that. So it's very clearly associated only on Earth with places like swamps. And it turns out, this is a great literature for me, there's a very nice study of penguins on one of these Antarctic islands, and you can use phosphine. It's produced, it's actually the bacteria in the guts of the penguins. So of course, they leave waste on the ice, and you can measure the phosphine, and I suppose tell something about the health or number of the penguins. So I believe I checked this, they're the Gen 2 penguin, this kind of penguin. So it's very nice to read these papers from a different scientific discipline. So I'm a radio astronomer, and the reason this approach to Venus has not been taken before, I think, was because certainly in the UK, there's a small number of astrobiologists interested in the solar system, and I think none of those are also radio astronomers. But when I was looking at this idea of looking for phosphine in planets, I realized we don't actually need this future far infrared space telescope. One of the transitions, that the quantum transitions that the phosphine molecule undergoes is actually at a wavelength of 1 millimeter. And if you have a radio telescope on a sufficiently high site, a high dry plateau or mountain, you can actually observe that already because these telescopes exist. So I looked for the, I think that's not rotating about the right axis, I'm sorry, the lowest ground state transition of the phosphine molecule. I approached the James Clerk Maxwell telescope, which anyone in the world can do with a project requiring only a few hours, and the staff will carry it out remotely for you. So that was what they did for us in 2017. And in our proposal to the telescope, I argued that it would be possible to get down to astrobiologically interesting levels of phosphine compared to, at that time, a very wild estimate, a guess really, of the amount there might be in Venus' atmosphere if there were microbes. So the idea is, I should have mentioned this earlier, although the surface of Venus today is very hot and hostile due to a runaway greenhouse effect, then that presumably would have taken place over millions of years, and there might possibly have been time for microbes to adapt to an aerial existence and move up to a possible habitat in the high clouds. So this was astronomically possible in the sense that the telescope had already verified, for example, this example of looking for sulfuric acid vapor at such an upper limit, but you can tell they were able to observe a small absorption line down to a few 10,000ths of the strength of the continuum for a molecule with not very many transitions. So the level populations are rather concentrated. The absorption should be favorable for a few parts per billion. And that was the case we made. Okay. So when we actually got the data with this little receiver here, which is now retired from the telescope after 20 years of service and has been replaced by a new one, so it's very exciting if we get more data. But in 2017, we obtained this data set. So what you're looking at in the middle is time is on the vertical axis, and spectral channel, so wavelength or frequency, or equivalently Doppler shifted velocity, is on the x-axis. And all you see really is these vertical stripes, bright and dark stripes. And these are unfortunately due to the fact that Venus is very bright, even at radio wavelengths. And the signal bounces around reflecting surfaces around the telescope and re-enters the signal processing chain, and then it appears at a signal at a slightly different frequency where it shouldn't be. And so you get these waves across the passband. So on the right, we see the signal that's just from that bottom box of spectra turned into a brightness against Doppler shifted velocity plot. And you see these big undulations, and these are required to be taken out in a series of steps. So just in this one observation, the thing we were looking for would be where the darker black shaded spectral channels appear in the bottom right plot. So you can see there's an awful lot of noise going on. The overlaid one is a Fourier transform to try and characterize the noise, but you can see from the panels on the left, it changes between observations, and that's really hard to do. So this was not very promising for about 18 months until I found some time to work on it more intensively. And I realized we probably did have about a 5 sigma detection of this absorption line, and it did appear exactly at the velocity of Venus. So it's not an effect from the terrestrial atmosphere or another frequency associated with a different transition of a different molecule, for example. But the exact signal to noise was a bit uncertain because we have to fit these functions to remove all these ripples in the spectral baseline. And so it can be argued it's a bit subjective how you do that. But it was very promising, and my colleague Hideo Sagawa at Kyoto Sangyo University in Japan kindly ran a radiative transfer model for us to say if there was phosphine molecules in the high clouds of Venus, what would the absorption line look like? And that's the dotted red line. And then if we process this in the same manner as the real data, we get the solid red line, and we get a really nice fit to the line depth and width. If the phosphine is present in a trace amount of about 20 parts per billion, and that's really small, that is quite an achievement for the telescope, but the actual amount is not too uncertain. It does depend a little bit on a collisional broadening coefficient for molecules of phosphine in a carbon dioxide gas mixture, which has never been measured because on Earth it's not a useful thing. But by making some small extrapolations from ammonia molecules, for example, we were able to come up with a reasonable range of constants, and so we arrive at this figure of 20 parts per billion. Okay, so really a trace gas, as you might expect in an astrobiological context for a small biosphere. Okay, so armed with this, we were eventually successful at, I think, our 4th attempt with the much newer ALMA network of telescopes in Chile, which can observe the same transition at the same wavelength. And eventually the director awarded us some time. I think we used 1.5 hours of time on source to look at Venus with the power of these 45 telescopes, and also with the better spectral resolution of the array to try and get a map of the distribution of phosphine across the planet. And this is the attempt. These all in white are the figures from the paper, which is open access, incidentally, if you want to take a look. We thought the distribution across the planet as well as the detection would be very interesting, but the data are extremely difficult. Again, the problem is essentially that Venus is too bright for these powerful telescopes, and that introduces signal artifacts. Unfortunately, there was an unknown problem with the connections between the telescopes on the shortest spatial baselines between them. Those spectra were extremely ripply, so much going up and down, much more than any one of these, and that particular part of the signal chain had to be discarded. So you can see it doesn't look very promising. We will be looking in each of these spectral boxes for a nice little dip representing absorption in the middle, but they all look kind of random, and especially around the edges of the planet, you can see they look really scruffy. And that's a result of the signal gradient, I think, at the edge of the planet. So ALMA did very well to do this. It's not something that is the major science of ALMA, observing solar system planets and large objects in general. And so although we had to remove part of the data, that was the only unusual step we did in the processing. We did also have to ask all the experts there for ideas. But essentially, we were pushing the capabilities of what the ALMA telescope network could do very much. And we have, in fact, achieved nearly 2 orders of magnitude better sensitivity than what is formally the specification. So that's quite an achievement. And I should say that's particularly the second author of the paper is Anita Richards at the University of Manchester, who is an ALMA staff member. And so it took all her skills and the staff skills to get this result for us. Okay, so the final result, the spectrum of the whole planet, JCMT only sees the whole planet, and for ALMA you can collapse all that data I just showed you to make a spectrum of the planet as a whole. And this is what we got. And indeed, ALMA did confirm the spectrum, the tentative spectrum in yellow that we had from the JCMT. Okay, the backdrop is interesting because it's an ultraviolet image showing these dark streaks at a particular ultraviolet wavelength that is thought to come from transient microbial sized particles. So I just use that here as a nice backdrop, and also because it shows the illumination of Venus in this case a bit as it was seen by ALMA and JCMT. So there was a dark crescent on one side. Okay, so we're looking just at a histogram here going along in wavelength or velocity, and you can see the characteristic dip where the molecules absorb and remove the light at the wavelength characteristic of the phosphine molecule. So this was incredibly exciting. We had this by about the middle of 2019, and the two spectra making a modest account of the fact that ALMA loses some of the signal from the largest scale of the planet in a way that was unavoidable for technical reasons, making a modest correction for that. The two spectra agree quite well in intensity, and they certainly agree in the width of the line. So this is really good confirmation. So for astronomers with such a deep observation, we've had to make a very strong case about the robustness. As I said, to make the spectrum look cosmetically nicer, you normally fit some kind of smooth function to all this systematic wiggle in the spectral baseline. But if you don't do that, if you just literally take the whole planet spectrum from JCMT and put it on top of the one from Venus, you should be able to, the one from JCMT and the one from ALMA, sorry, they're both from Venus, you should be able to see the only feature that reproduces is at the line velocity and has the right line shape. And otherwise, as shown by these red bars, you get signals that are randomly different for the telescope artifacts from the two observatories, and so there's no agreement. And nowhere else in the spectrum, maybe there are two adjacent spectral channels that agree by chance, but nowhere else do you get this double signal representing the line. So I think we can rule out a false positive, false negative, whatever you want to call it. Okay, we were also able, there's a lot of passband, a lot of other wavelengths with the ALMA data. We were able to process some of that where there is no line at an offset frequency and say, does this technique of trying to remove this unfortunate undulation pattern, does that make a line? Is that an artifact of the processing? I'm sorry, I've gone up a page by mistake. And that's not the case. You can make, again, a couple of spectral channels look slightly negative, but nothing like the real line. Okay. So the next question was, we talked to a few people, they were very skeptical. They said this molecule is so unlikely, it must be another species. So we looked at catalogs of all molecules, not even just in an astronomical context, but an industrial context or something. So there's a table in the paper. It's maybe not at all visible on your screens, but of course there's a lot of transitions known of complex organics, for example, but they have many, many, many transitions excited at high energies and so on, and will be very unlikely in the cool upper clouds of Venus. And if they were there, you would see a whole family of them, for example. So these species are very unlikely, with the exception of, there's a transition of sulfur dioxide, which is not a particularly favored one, because the level population will be excited at about twice the temperature of Venus clouds. But we did look at this very carefully, and that's the green curve on the right is the maximum contribution it could be making to our phosphine line. And we know that's a maximum because we had a simultaneous observation given ALMA's wide passband of two other more favorable sulfur dioxide transitions. And one of those is shown in the middle figure. It's clearly not there. It would be at this is a rather nasty bit of data not with any corrections, but it would be where this solid black line is. It's not there. In order to mimic the whole presence of phosphine, this other sulfur dioxide transition would have to be as deep as that very deep kind of like, always looks to me like the blade of a sword, this one here. So you can see something like that will be totally visible in our data and is not there. So with simultaneous observation, given that sulfur dioxide in Venus atmosphere is somewhat variable, we can say we have a very strong way to remove this contamination, and it's not more than 10%. So we think we really do have phosphine. Okay. So what is interesting about this to me as an astrobiologist particularly? Okay, so at this 1 millimeter wavelength, the clouds are completely opaque below an altitude of about 55 kilometers. And it's actually, because there is an opaque quasi-continuum signal there, which is actually a blend of very broad emission lines from other molecules, such as the carbon dioxide. So we know that our phosphine, to be absorbing against this continuum, and this is its probability distribution function, the phosphine must be above that. And that places it in the high clouds, maybe between 55 and 65 kilometers. And this is of real interest because this is the upper part of the proposed habitable zone, as shown in the lower middle figure. And if you read off, for example, 55 kilometers for this standard Venusian atmosphere, the temperature is 20 centigrade and the pressure is about half a bar. So really quite similar to the surface of the Earth. And that's why there are long-term suggestions it could be a habitat. It's a very exotic potential habitat, so the wind speeds are extremely high, as the sketch shows, and it's extremely acidic. So it's a very challenging possible habitat, but it is of interest. We can't, unfortunately, we don't have enough signal to noise in the spectrum to turn it into an absolute measure of the height, but we hope we could do that with a future observation with ALMA. And also it is possible in the atmospheric chemistry that the molecules are produced lower down and drift upwards. So it's not conclusive in the habitable zone, but it is interesting. The other thing that's very interesting to me is there was already a prediction that if there were any floating microbes in the clouds of Venus, they would have their most stable period in the Hadley circulation cells shown in the diagram in the upper right. So as they circulate around that pattern, they would maybe spend 30 or 40 Earth days exposed to sunlight before sinking, before reaching the polar caps. And so it might be that's the latitudes on the planet where the phosphine production is most favored, if it's produced by by microorganisms that are reproducing. And therefore you would not expect to see phosphine at the poles because the source would have sunk before the gas in which they were born reached the poles. And that's actually what we saw. So the polar caps, there's a flat line spectrum, no absorption. The equatorial one, I have to say, is rather uncertain for technical reasons to do with this sensitivity of ALMA to large scales, particularly across the fat equator of the planet. But there's a very strong signal at the mid-latitudes. So again, that's really exciting to me. Okay. So the overall results from the observations, the phosphine is confirmed as present, and given the uncertainties in the physics, something like 10 to 30 parts per billion is probably the most likely. That's reasonably well constrained. Hints that it is there at conditions of roughly Earth's surface temperature and pressure, and a strong conclusion that we can't detect it at the poles. It's considerably depleted in the polar caps. And I think very interesting is that the regardless of how you play with this idea of the filtering of different scales with ALMA, the two line depths are consistent within a factor of 2 to 3. And we wouldn't expect highly seasonal effects on Venus. So along with the fact it doesn't have an extreme planetary tilt, the atmosphere super rotates at these altitudes, so a gas molecule will come round again to the same position within about 4 or 5 Earth days, and so everything is really probably smoothed out in longitude and over time. And so although our observations excuse me, were taken nearly 2 years apart, we would expect rather similar amounts of phosphine, and that's what we see. Okay. So my colleagues at MIT and Cambridge University in the UK have done all the chemistry side of the project. And it was really great to work with them because I was really struggling to understand any of this. So particularly Paul Rimmer in Cambridge used his photochemical model for planetary atmospheres and worked out that the formation of phosphine molecules by abiotic excuse me, non-biological sources is really, really small at all altitudes, whereas the destruction is much faster, as shown by those red and blue curves. If you make a total upper limit from all the photochemical processes at any height, as shown in the right panel, you can't achieve more than, well, in the clouds, about 10 to the minus 15 parts of phosphine. Whereas if you introduce some unknown source at 10 to the 7 molecules per square centimeter of cloud area per second, you can produce, I think this is a 10 parts per billion model at the lower end of the range. So it's possible, but you do need an active source or the phosphine would all be destroyed. So William Baines and Janusz Petkowski of MIT led the overall approach to the chemical modeling. So as well as the photochemistry calculated in the atmosphere, there are thermodynamical calculations for all the compounds we know of in the lower atmosphere, and also calculations based on rock chemistry in the surface. So for example, small bits of mineral could blow upwards, or gases could drift upwards and end up in the clouds. We also considered, I will show in a moment, those processes were not favorable. So we considered processes to which there would be a positive energy input, in particular something like a massive meteor strike or a volcanic plume coming up for the surface, since there is an idea that phosphine can be a product of volcanochemistry. Okay, and really surprisingly to me, it was very clear cut. In spite of thousands and thousands of calculations, all of these processes fell short by 10,000 times or more of the amount of phosphine we need to be stably present in the atmosphere. So there's a 103-page companion paper on the chemical calculation. If you want to look on the archive, I think I have the link in the next slide. But here's an example of phosphate mineral to phosphine is a possible production route that's very obvious to chemists. And the chemical route on the left is shown, and you can see there are red lines on it, and those are the ones where the rate is so slow it essentially acts as halting the process to get you on to further stages, which would eventually make phosphine. You can see there are some dotted lines in there, and the caveat is that some of the necessary reaction rates have never been measured in the lab, and that's generally because of the dangerousness of working with phosphine chemicals and they're not being useful industrially. So some of those processes we use a nitrogen compound instead. But the network is very conservative. Only forward reaction rates are used, so we're trying to push for as much phosphine as possible, and not including any of the destruction, the back reaction rates, and we still can't make, with any reasonable conditions, we still can't make phosphine. So this heat map diagram is showing why. So the colors are just showing the numbers of reactions and conditions that were tried. And on the bottom axis is the energy associated with the reaction. And essentially, none of them release energy. So the left-hand part of that diagram, the part below 0, where it would be an exothermic reaction, is all black. There are no conditions and reactions where the phosphine will be spontaneously produced, which is quite surprising. So different to where it's driven by high temperatures and hydrogen. On Jupiter, for example, none of this is possible in any Venus conditions that we know about. And again, we were very conservative. There is one upper limit and one measurement of phosphorus of unknown chemical compound from the Soviet Vega 2 descent lander. Gave the measurement in 1985. It is uncertain because obviously it was an instrument battling very difficult conditions, but we took that as the amount of phosphine available as the most conservative, and we still can't make this work. Okay. The photochemistry, I should also point out the uncertainties here. So this is Paul Rimmer's plot. So the model was validated on other molecules known to be present in Venus atmosphere. So those with order of magnitude estimates of the abundance and the heights, some example heights are shown by the data and the error bars, and then the outputs of Paul's curve model are shown by the curves. Okay, so the model validates as well as can be expected on other species, and the inclusion here is the phosphorus chemistry. There are one or two anomalies. I think molecular oxygen is not well explained in anyone's model as yet, so we have the same some slightly enigmatic results as anyone else in the world, but it does validate, it checks out. Okay, there's been a lot of interest since we published the paper, and we're about 3 weeks in now, on the idea that phosphine could be a product in volcanic plumes. So this plot is showing the possible combinations of volcanic conditions and the outgassing rate compared to the amount we would need, which I believe is the red line. And there's a shortfall of at least 200 times. So there is evidence of volcanism on Venus. There's even one spacecraft image from orbit showing a transient hotspot that was probably a large active volcanic flow. But if we say more than 200 times as much volcanic activity as the Earth today, that would be something like 30,000 active volcanoes. It would be much worse than the most volcanic episode, such as the Deccan Traps period, for example, that the Earth has ever undergone. And I think that would be very noticeable in other effects in the atmosphere. And also, again, that's extremely conservative. It assumes that there's lots of hydrogen available in the rocky minerals in the volcano, and that there's quite a lot of water in the volcanic plume, and neither of those is actually correct for Venus, where the surface is obviously very dry. So we may have a shortfall of billions. The other injection processes that bring their own energy to the process, the yields are tiny. I'm not used to calculations done in grams per second per planet, but apparently that's we can really strongly rule those out. So the idea of life, and we really can't say this is evidence for life, but it's very interesting. So obviously there are extreme challenges for the survival of any organisms on Venus. So one thing that we were able to sanity check is that the peak production, the production rate shown in Paul Rimmer's plot earlier, would not be challenging for anaerobic microorganisms that operate something like the way they do on Earth. In fact, they'd only need about 10% of the peak productivity that's actually measured for Earth bacteria. And that includes them operating in Venusian conditions. So whether they could actually do that is the challenge. There is really no analog habitat on Earth, nowhere where organisms have needed to evolve for anything like these conditions, probably something you're much more expert on than I am. But it's, say, 50 times drier in the clouds than even the high deserts of the Earth. And it's the droplets, which are a mixture of things that have liquid phases, something like 90% sulfuric acid and 10% water. And that's incredibly corrosive. So there is previous work suggesting that organisms could build little shells of maybe abundant sulfur atoms around themselves or something, which raises the problem of, you know, how do nutrients get in and waste products get out? Something very much for future work. So William Baines has worked out that, as shown in this diagram here, thermodynamically, that you can come up with a route for an organism to operate energetically inside a water droplet, a water and sulfuric acid droplet, and have phosphine as a byproduct. It's the actual survival that is extremely difficult to imagine. So there is a paper out, a companion paper out on this. I won't talk about this in very much detail, but this was led by Sarah Seeger at MIT, who's a very well-known astrobiologist, and it proposes that there could be a life cycle, and it lays out all the hazards for organisms with such a life cycle in the clouds of Venus. So with them having evolved upwards at some point, hundreds of millions of years or more in the past from the surface, they would have to be entirely dependent on what's available in these very high cool clouds, and independent of the surface unless there are nutrients diffusing upwards, for example. But you can imagine a water droplet in the clouds, a size a few microns perhaps, with a very small colony of microbes inside, you know, tens of microbes or a few microbes in each water, in each droplet. As that grows like a raindrop, it would settle out and come down, but it wouldn't come down like rain because it's hotter lower down. So that would evaporate, leaving possibly a desiccated spore of the microbe in a dormant state to be carried upwards again into the clouds and end up in a new droplet. And so it's possible to imagine how this would work, provided they have survival mechanisms. I encourage you to look at the paper on that for all the details where the challenges in particular are very much laid out. Okay, I'm nearly at the end, in fact, so hopefully there'll be lots of time for questions. Very excitingly to me, a paper came out, which was a big surprise to us. So a team in America have gone back and looked at the mass spectrometer data from Pioneer Venus, which is, I think, NASA's only spacecraft measuring conditions in the atmosphere of Venus in 1978. And so the forget what the L stands for, but neutral mass spectrometer, actually took measurements at this rather vital altitude range of 50 to 60 kilometers above the surface. And of course, it detected very abundant things. So I think the mass peak of 28 in the diagram is carbon monoxide. That's what you'd expect. But they find evidence at the right mass with a very high mass resolution for phosphine. And they believe they can distinguish it from the compound H2S, both on slightly different mass grounds, taking into account the isotopes of both, but also in particular taking into account both of these molecules would have deuterium substituted isotopes, and they do have hints of PH2D, but not of HDS. And I think the HDS is ruled out by 2 of its possible masses and another instrument. So these are very small counts for this instrument, but counts at a level that have been published before as of interest and as detections. So this, from a completely different technique and an old data set, is very exciting to me, and gives us more of an idea indeed of the distribution of phosphorus in the atmosphere. Okay, so I think I can wrap up just to give you an idea of where we're at. So the little plot is a snap of an email I exchanged with another British person, the support scientist at the telescope, and you can tell we were joking about this project, about there being a Nobel Prize at stake, because we really did not expect the detection. We expected an upper limit on phosphine that would be interesting to other astrobiologists in terms of production of acidophiles. We really weren't expecting a detection. So now we are working particularly hard on the chemistry. So we have asked anyone with ideas basically just to email them. It's now actually more like 3 weeks. And although people have sent us lots of emails about the chemistry, most of them are slight variations of what we've already tried. And we can't make enough phosphine by that, by any of those routes. So we're fully acknowledging the life prospect is exciting, but there are incredible challenges for the idea of life in the clouds, which has just been this not very much tested hypothesis. And now I think it's really time to see on the biological side if this is in any sense possible. And then more on the space science side, very excitingly, various space agencies have for a little while now been interested in return to Venus. It's incredible how we're reliant on data from the 1970s and 80s, but with the examples, with the progress in much more modern materials technology and data transfer rates and so on, really hoping a space agency might be able to, or multiple ones might be able to send something again to Venus. In particular, Rocket Labs, the private company, and here's a launch of its Electron rocket. So it's a real launch. They really do have rockets. They're interested in getting a tiny payload to Venus by about 2023. So I think there's an awful lot to watch. Okay, I think I will try and stop sharing. And thank you very much, and take questions.
Thank you, Jane. Thank you very much for this nice presentation. So are there any questions? Yes, I have one question. Yes, I think, can you unmute your microphone, Fernando? Yes,
yes.
Go ahead.
Possibly your video, so I'm not looking at a random part of the screen.
Okay.
Go ahead.
Hello.
Hi.
This is Fernando. I'm a PhD student of the University of Alcalá. This is not totally for sure my field. I'm doing heliophysics. And first of all, thank you very much for the nice talk. And I wanted to know if you consider the contribution or the probable contribution of the cosmic rays or the interaction of the solar wind with the atmosphere for the production of the phosphine.
Yes, so Lewis Dartnell worked on that, so you're probably familiar with some of his work, but I'm not sure it was all published. So this is actually one of the avenues we're exploring. I think it was more considered at the time when he worked on this in about 2015, and whether the cosmic rays were destructive for organisms. But as a driver of the chemistry, my understanding from interstellar medium chemistry, and maybe Isa's knows more about this, is that some of the reactions are not well understood, but it's certainly an avenue we would want to consider. I guess we could benchmark that on the Earth, because apart from slight differences with the solar wind interaction, I guess one could test things like the impact on the Earth's aerial biosphere. Yeah.
And with the solar wind, because here we have the magnetosphere, but Venus, I think, is less or less strong than it could be here.
Yes, so I'm not sure at what height the solar wind is essentially deflected in or stopped at the Earth's atmosphere compared to the height it would be in Venus' atmosphere. That's something we would really need to think about, because Venus' atmosphere extends up to about 100 kilometers in a very thin state. Not sure exactly where they would be comparable.
Okay, thank you.
Thank you. Are there other questions?
Hello.
Hello, yes, go ahead.
Thank you, Jane, for this exciting talk.
I'm sorry, I can't hear you very well at all.
Can you speak louder?
Sorry. Yes.
Now,
How
yes.
much better?
Thank you.
Thank
Yeah.
You're welcome. Excuses. So thank you for this exciting talk. I was wondering, I think you already answered a specific question I had previously, that is concerning these claims that some kind of volcanic activity could explain this phosphine detection. I don't think so, and it seems from the paper I recently read and your own talk today, there is clear not evidence for reactions, inorganic reactions, doing particularly in so extreme environment. And the second related question is if you have studied the possible effects of meteoroids penetrating in the atmosphere, because this is a region where ablation, particularly of carbonaceous chondrites and iron meteorites, could bring some phosphorus. And of course, the same happen, because if the reactions are not favorable, then please tell me. Thank you.
Yes, those are both very good points. And we have had queries about both of those. I apologize if one of those emails was from you and we haven't answered you yet. The ablation of meteorites, somebody mentioned to us, and then the plasma surrounding the meteorite would be really interesting chemically. I think it's the same problem as for the volcanoes, where, for example, it's been suggested, phosphides would be more favorable chemically. The calculations so far suggest it's just essentially the amount of phosphorus in however favorable a form. So we know what it would be likely to be, as you say, in meteorites, the similar ones that hit the Earth. There just isn't enough. The surface question, I think, because we don't have mineralogy at the surface, is less certain. It's hard to imagine if Earth and Venus formed in fairly similar ways, that for some reason there are much more phosphorus-bearing minerals on the surface than there are on the Earth. But this is something, again, we really need the experiment to tell us. What was I going to say there? In terms of the phosphorus available for chemistry and as a possible nutrient, apparently microorganisms are phosphorus limited in most Earth situations like swamps. So they'd probably be more productive if you gave them more phosphorus. And the data we have on the clouds of Venus is actually quite a lot of phosphorus, I believe, relative to what's available, say, in a swamp on the Earth. So yeah, we're trying to balance all these things, but just the bulk numbers are not very favorable at the moment.
Thank you. And greetings from the Institute of Space Sciences in Barcelona.
Greetings to you.
Same to you.
Okay. Are there any other questions? Yes. Go ahead, Ricardo.
Hello. I'm trying to switch on my camera. Hi. So, very nice talk. Very exciting, especially for all the people that work on Venus atmosphere. I had the pleasure to work on the Venus Express mission for many, many years. So
it's great. We really want to talk to Venus Express people. Yes.
It's very exciting to see again a renewed interest in Venus atmosphere. So my question is about the possibility to find temporal variability of phosphine in the atmosphere. So temporal variability linked, for instance, to the variability of the atmosphere in the winds that we know that change a little in different seasons, in different periods of time, sorry. And then also, if you kind of make observations at different phases of Venus with different illuminations, because I'm not sure if and there is a big constraint from the observations to do this kind of search for temporal variability.
Yes, so we wanted to look at this without ALMA data because I think we had about 20% dark on the planet and 80% illuminated, something like that. And I wondered if there might be a gradient if the phosphorus production is very quickly shut off as if the source material is moving into darkness. Unfortunately, there's a technical reason. If you take spectra down the thin crescent of the planet, they're dominated by the edge effects, which are different to the effects in the middle of the planet. And so you really can't compare the spectra reliably. I think we know the reason for most of the issues, the technical issues, and we're hopeful that when ALMA is up and running again, they're in a difficult COVID situation in Chile, we would be able to do a more sophisticated observation, and that would be really interesting. So in terms of time, that would also be related to the time. So for short-term effects, obviously we could sample over hours. In fact, we have 2 observations about an hour apart, so we could look for the very short-term effects. And then I guess it takes about 2 Earth days for the material to cross the visible face of the planet, so we can look for variations on timescales. So monitoring will be very interesting. So the real Venus experts on our team are Hideo Sagawa, who advises he thinks things will be pretty smooth. And then the upper atmosphere expert is Inga Moela-Wadag at Imperial. And so we are working a bit more on that. Unfortunately, don't really have the data at the moment.
Thank you very much.
Thank you. Are there any other questions? No? I have a couple of questions myself.
Great.
So the first one relates to the fact that phosphine is highly reactive. And I think there are, probably measurements or estimates for how phosphine reacts with hydrogen, for example. And then at least that's what we know for the interstellar medium. So phosphine disappears rapidly, very fast.
Yes.
I was wondering whether your estimate of the 10% of contribution of these anaerobic microorganisms, whether that estimate takes into consideration, considers that phosphine is reacting very fast.
Yes, so Paul Rimmer is updating the photochemistry model at the moment, so there will be a second paper on this. He had to very quickly make a model for us, so there will be some small refinements to that. So the model already includes the fact that there's upwards diffusion. The measured and inferred speeds of that are included, and I think that turns out to be the dominant effect. So the phosphine drifts up to an altitude of, say, 80 kilometers. The destruction timescale there is really short. It's 1,000 seconds or less. Mm-hmm. The destruction timescale in the middle atmosphere is not certain because we don't know the abundances of the radicals. Apparently chlorine is really important, mm-hmm. But there's no data on it. But the diffusion timescale is shorter. So regardless of not knowing the chemical destruction timescale at all altitudes, we do know the overall rate at which it would be destroyed. Did that answer all of your question? I may have missed a part.
Yeah, I mean, so Paul is basically updating, the chemical code, I guess, with all these, so with all these destruction routes, I guess. So
yes,
whether phosphine could remain in the amount that you predict or that you measure, so that it can be detected, I guess. No?
Yeah. So the production rate. So the 10 to the 7 molecules per square centimeter per second is including as much of the chemistry as we have it, and particularly with this rapid destruction at high altitudes and the upwards diffusion. And this is all buried in the last few supplementary figures of the paper. Yeah. So where the 10% efficiency of the organisms comes in is the maximum production rate observed on Earth is 10 to the 8 per square centimeter per second. So roughly for the purposes of getting the point across, we've said they don't even need to be 10 to the 7 versus 10 to the 8, 10% of peak productivity that's possible for earthly organisms. But that really is like an order of magnitude one.
Right, okay, so in principle, even considering the destruction processes for phosphine, it would be enough. So these microorganisms will be able to create enough to detect the level that you are measuring.
Yes, if the destruction is faster, then the rate would have to be higher, but you could make it, the controlling timescale could be 10 times shorter, and you'd still be at what Earth organisms can do. But also, if this argument about a more phosphorus-rich environment is correct, then it may be that the productivity could anyway be 10 to the 9 or 10 to the 10 or something. Mm-hmm. I think probably, chat with Paul about that.
All right. Okay. I may drop him an email. All right.
That would be great. Yeah.
And then the second question is about, you showed a table with all the possible contaminants of the feature, for the phosphine feature. Mm-hmm. But I don't remember now very well, but I think I didn't see one possible species, which is silicon sulfide. So there's another detection of phosphine in a circumstellar envelope that was reported by Marcelino Agunde.
Yeah, that's IRC 10216, I think, isn't it? Yes. I have read that. Yeah.
Yeah, and then so they reported the spectrum of phosphine together with some contamination from silicon sulfide.
Yes, I remember now. We were asked about this. It's the transition that's close, and it's actually not very close. I think it's about 3 kilometers a second off, and this is in the supplementary information. It's from one of the vibrationally excited levels. Mm-hmm. So it can be populated, it can be pumped by the infrared of a star, but it's, I forget, it's like 1500K, 3000K. There were a couple of vibrational lines of molecules that people suggested, of which that's one, but it certainly doesn't agree in terms of the level populations, and it also would be pretty different in terms of velocity. Our best uncertainty on the line velocity is, I think, 0.3 kilometers a second, so it would be like 10 sigma off in velocity.
Okay. Mm-hmm. Okay.
Because the lines are quite narrow also, unlike IRC 10216. So.
Yes. Okay, thank you. Is there any other question? Miguel?
Quizás puedo. Yes. Okay. Yes, thank you. Thank you very much for the talk. Very interesting and very interesting results indeed. Just one technical question. You said that you are going to do follow observation in ALMA whenever it's possible. Are there any other transitions reachable with ALMA that could confirm the phosphine detection, or with other telescopes?
Yeah, this is where the wide separation in frequency of the telescopes is not helpful to us. So ALMA can nominally observe the 3-to-2 transition, but it's in ALMA band 10, I think. And we worked out it would, because of the low atmospheric transmission and the need to go deep, it would take something like 10 days of ALMA time. And we were asked to check, what about if the weather was exceptionally good? And I found, the best weather that we would possibly ask for, if all other the projects were stopped had only occurred for like 8 hours in one interval or something last year. So I think it's probably practically impossible. That's the advice I get from Anita Richards. The other one of interest is the 2-to-1 transition, which Sophia, the airborne telescope, could do. It's difficult because the telescope is not very big. And also they have a sun avoidance angle, presumably so the pilots don't crash the plane while trying to fly the telescope towards Venus. It looks technically possible, and I was going to ask for that. It'd have to be done when Venus is quite large or the beam dilution kills you. But they had to ground the plane at the start of the pandemic, just at the point where we really were in a position to ask. So I think all these things, Venus is receding. It'll become an evening object again in about a year, and I think everything will be ready for an observational campaign much better then. Some infrared observations sampling the upper atmosphere are already in, and those give us a really nice constraint on the photochemical destruction, in fact, but the millimeter far infrared is very difficult. That's probably far more detailed than everybody else wanted, but that's the situation.
Okay, and just one question, one comment. There has been some controversy about the discovery, whether it is really phosphine, whether it really means there is life on Venus, where whatever it is. Well, yeah. Maybe in the future we find some traces in exoplanets. The quality of the data will be probably even worse than yours, and the analysis of the data will be extremely difficult. Do you believe that the community will believe on these results if we find something in an exoplanet?
I think it's a lot of people have said that actually this is a really good benchmarking case for exoplanet science, because if you'd found a molecule on an exo-Venus, everybody would have gone, well, obviously that's got to be some natural source. But now we have an actual Venus we can sample, and maybe even send life detecting technology that works really well as a benchmark. In a particular case of phosphine, so my colleague Clara Sousa Silva has just published a paper on this. She thinks it will be detectable with James Webb Space Telescope in the infrared for maybe rocky planets with very thick atmospheres around M-type stars. Otherwise, even for gas giants, it's really difficult to detect. To be honest, we're really struggling with our own Venus, which is like 0.3 AU away sometimes. So something light years away. I think it's going to be very difficult, but there are obviously stronger biomarkers for exoplanets, and the subtle combinations of methane and oxygen that we can benchmark to Earth history. My gut feeling is maybe that's better for the exoplanets.
Yeah, I agree. Thank you.
Thank you. Are there any other questions?
Was there a question in the chat? Is this going to something like pass?
Right. Okay. Let me see.
Maybe this is someone already.
That was Miguel, I think.
Okay. So we're done.
Okay. So no other questions. Okay. If there are no other questions, then thank you very much, Jane. Thank you very much for joining us today. I'm sure that you're very, very busy.
Well, it's my pleasure to talk to an audience interested in astrobiology instead of an audience of skeptical astronomers. So, so please send me any more questions in an email if something occurs to you. So.
Yeah, definitely. So if anyone really wants to send Jane any email, then contact me, and then I'll give you her email address.
Please.
And thank you very much, Jane.
In other cases, Jane, we would have invited you to lunch here in Madrid. But
I could just imagine the wonderful lunch in the future.
Maybe another time in the future. Once the situation improves, then we'll definitely get you here.
I will love to. It would be great. Okay, thank you all very much.
Thank you very much. Thank you very much, everyone.
Goodbye.
Ciao.
Talk to you soon. Bye. Bye.